The first physical quantity we can model with kinetic theory is pressure. Pressure is just the force per unit area on the walls of the container. We can write pressure as P equals F divided by A. F being the force, A being the area upon which the force is applied. Now, recalling the impulse momentum change theorem, we can find the force from the change of momentum. F equals delta P over delta T. So we'll begin our derivation by finding delta P and delta T for a single molecule colliding with one of the very massive walls of its perfectly rigid container. Let's begin by finding the momentum change during a single collision of a molecule with a wall of the container. This is just the momentum change perpendicular to the wall, as can be seen in the figure to the right. Now, since in the ideal gas model all collisions are elastic, it follows that the perpendicular component of the momentum only changes in sign, not in magnitude. And as a consequence, the change in momentum in that perpendicular direction is just twice the magnitude of the momentum perpendicular to the wall, or 2 times m times the magnitude of the velocity perpendicular to the wall. We've just established the change in momentum of a particle after it collides with the wall of the container. Now we need to determine the amount of time between those collisions. That is delta T. Now delta T is the time it takes for the particle to travel from one side of the box to the other and back again. So if the box has an edge length of L, then it's the time it takes for the particle to travel to L. Now the way we can put this is 2L is equal to the component of the velocity perpendicular to the wall times the time between collisions, delta T. Rearranging this, we get delta T is equal to 2L divided by V sub x. Well, the time between collisions is very small, and combining what we've gathered so far, we know that the force on the wall is delta P sub x over delta T. We found that delta P sub x is just 2 times mv sub x, and we also found the time between collisions, delta T, which is 2L divided by V sub x. If we combine all of this, substituting for delta P and delta T, we find that F sub x is equal to 2mv sub x divided by 2L divided by Vx, or mvx squared over L. To calculate the force due to all the molecules in the box, we have to add the force contributions from each molecule. That results in the following expression, that the force on the wall is equal to the mass of a single molecule divided by the edge length of the box, multiplied by the sum of the square of the x component of velocity of all the particles in the box. Now, we can define the average value of the square of the x component of velocity in this way. We use a bar to signify average, and we get the average of Vx squared is equal to the sum of the Vx squares for all of the particles divided by the total number of particles. We can rearrange this so that this sum of n particle velocity, square velocities is just n times the average of the square of the x components of velocity. That gives us a simplified form for the force. F sub x equals m divided by L times the number of particles times the average square of the x component of velocity. The average square of the velocity in one direction can be related to the speed using the Pythagorean theorem, much like finding the length of the diagonal of a box. the mean square speed, over here on the left, is just equal to the sum of the squares of the velocity components, Vx squared mean plus Vy squared mean plus Vz squared mean. Since all molecules move in random directions and there's no preference between x, y, and z, we can write the following, that the averages of the square of the components of the velocities are the same in all directions. Vx squared bar equals Vy squared bar equals Vz squared bar. So if we refer back to our expression, to our first expression for the mean square speed, we have that any one of these is equal to 1/3 of the mean square speed. So we can rewrite the force on the wall. The force is equal to the mass divided by 3 times the length of one edge times the number of particles in the box times the mean of the square speed. And then if we recall that the pressure is just force divided by area and that the volume of the box is just going to be the length of an edge times the area, we get the following, that the pressure is equal to 1/3 the mass of a particle times the number of particles in the box times the mean of the square speed divided by the volume. That is, the pressure in an ideal gas is directly proportional to the average square speed of the molecules. For all the derivations that we've done, this is the first important equation. Now let's use kinetic theory to find the average kinetic energy. Since the average kinetic energy would have to be the mass of a single particle, since they're all the same, divided by 2, multiplied by the mean square speed, we can rewrite our expression for pressure as follows, that PV equals 2/3 times the number of particles times the mean kinetic energy. And when we compare this to the ideal gas law that emerged from experiments, which is that pressure times volume is the number of moles times the gas constant times the temperature, or that pressure times volume is equal to the number of particles times the Boltzmann constant, which is given here, times the temperature, we can find that on comparison of this expression and this expression, PV equals 2/3 N times the average kinetic energy, and PV equals N times Boltzmann's constant times temperature, we get that the average kinetic energy, or the mean kinetic energy, is 3/2 kT. So the average kinetic energy of molecules in a gas is directly proportional to the absolute temperature. This is the most important result of kinetic theory. The higher the temperature, the faster the molecules move on average. So this, together with our expression for pressure, are now the 2 important equations that we've got from kinetic theory. Finally, we can use our result for the mean kinetic energy to find the root mean square velocity. So, our mean kinetic energy is just mass times the mean square speed divided by 2, but it's also equal to 3/2 kT. So, that means that we can find the root mean square velocity of a single particle. That is, VRMS, root mean square, is equal to the square root of the average square speed. And that's equal to the square root of 3 kT over m, derived from these 2 expressions. So this is the third of our equations, and it tells us that the higher the temperature, the faster the molecules move on average. So let's summarize the results of kinetic theory. The first is that pressure equals 1/3 mn V squared average divided by volume. That is, the pressure is equal to 1/3 times the mass of a single particle of the gas times the number of particles in the gas times the average square velocity of the molecules divided by the volume that the gas occupies. It tells us that the pressure in an ideal gas is directly proportional to the average square of the velocity of the molecules. The next finding is that the average kinetic energy per molecule is 3/2 kT, where K is the Boltzmann constant and T is the temperature given in kelvins, that is, the absolute temperature. Now, this tells us that the average kinetic energy of molecules in a gas is proportional to the absolute temperature. More to the point, it really defines absolute temperature in terms of the kinetic energy or the average kinetic energy of the molecules of the gas. It tells us that temperature cannot be negative, and it can only reach absolute zero when the average kinetic energy of molecules has reached zero. And then finally, we have an expression for the root mean square value of the velocity. And this is square root of 3 kT divided by m. And that's derived directly from the relationship that Ke is mv squared over 2, and that the average kinetic energy is 3/2 kT. It tells us that the average velocity of molecules depends on absolute temperature again, and it depends on molecular mass. It tells us that by increasing the temperature, the molecules move faster. Or conversely, the fact that the molecules are moving faster tells us that the temperature has increased. And the lighter the molecule, the faster it moves.